Good morning from Sydney. I'm Matthew Bracknell and I work with the Trustworthy Systems Group at Data61. I'm also a member of the Technical Steering Committee of the seL4 Foundation. I've spent several years working on the proofs about seL4, and today I want to share some of the things I've learned about them. If you have questions, please use the discussion board on the talk's virtual hub page. I'll be present there during the talk and throughout the summit, so please ask your questions as soon as you have them. You can also contact me via Twitter or any of the methods listed on my website. This is my first seL4 summit, so I've had to make some guesses about the audience for this talk. I guess that most of you are here because you're somehow involved in the seL4 ecosystem, building a product, providing a service, or pushing the boundaries of what's possible in trustworthy systems design. I guess that one of the things that attracts you to seL4 is the fact that it's formally verified. You believe that gives you strong assurances of reliability and security, and that's essential to your work. But I want to ask, what makes you believe that? I guess some of you have read the verification FAQs on the seL4 Systems website, in particular, the What We Prove page. If you haven't read these, then I certainly recommend that you do. If you wanted to go further, the TOC's 2014 paper also has much more detail about the verification. But even then, I'm not entirely satisfied with asking you to accept informal descriptions of the formal work. So I wonder if we can go deeper. But then I guess not so many of you have dug into the proofs themselves. So today I want to take some first steps to change that. Ultimately, I'd like you to form your own first-hand appreciation of the proofs and what they say about seL4. And so we'll take a tour through some parts of the proofs that I think will help you do that. I'll show you where to look and how to read those parts of the proofs, and I think you'll gain some insight into how the proofs actually provide those strong assurances. How do we do this? Well, we're going to look at a lot of code, but we'll focus on the parts of the proof that I think are the most interesting and also the most accessible. These are the abstract specification and the invariants that we prove about it. Here's a diagram that puts those parts in context. There are more proofs that are not shown here, but these are the core proofs that we call functional correctness. On the left, we can see the C kernel implementation and the binary produced by GCC. Above those, there is an implementation in Haskell, which is descended from the early prototype of seL4. For each of these, we have a tool which automatically translates the original artifact into a specification in the language of a theorem prover, where we can give it a formal semantics. The exec spec and C spec are in Isabelle whole, and the binary spec is in whole 4. Above those, we have the handwritten abstract specification in Isabelle whole. This is what we take as the definition of how seL4 should behave, and that's where we'll start exploring today. Looking at this whole column, we have a stack of specifications, more abstract towards the top and more concrete towards the bottom, and we also have a stack of refinement proofs between them. Refinement means that for every possible execution of a concrete specification, there's a related execution in the abstract specification. And refinement composes, so we get this from bottom to top. In other words, refinement shows that every possible behavior of the binary is permitted by the abstract specification. Finally, to the right of the abstract specification, we have a collection of properties that we prove about the specification, also in Isabelle whole. We call these invariants because we prove that they are preserved indefinitely by any seL4-based system. So we'll also spend quite some time looking at these. An important property of refinement is that the invariants we prove about the specification also hold down to the binary. This means we can learn a lot about seL4 just by looking at the spec and invariants. And of course, that's what we'll do today. We won't have time to look at the refinement or the details of how we actually prove the invariants, so we'll mainly be looking at the invariant properties themselves, what they mean, and why we need them. But one of the nice things about having machine check proofs is that you don't need to worry about the details of the proofs to believe what you can see has been proved. So that's the plan, abstract spec and invariants. But first, we'll have a short introduction to Isabelle whole, and then we'll work through some simple examples of how we can construct specifications and theorems about them. So let's dive in. This is the interactive mode of the Isabelle theorem prover. We have an editor window where we can work on our definitions and proofs, and we can also write queries which Isabelle will answer. Down below is the output window where Isabelle tells us things like the state of our proof and answers our queries. First up, you might be wondering, why are there so many double-quoted strings? Now, these are not strings. Isabelle is not just a single theorem prover, it's actually a framework for building logics and theorem provers. We're using Isabelle whole, which implements a fairly standard classical higher-order logic. But despite that, I'll mostly refer to it as Isabelle. But this design means that various things comes in layers, including the syntax. So these double quotes are actually a kind of bracket that Isabelle needs to parse that layered syntax. For reading the code today, just ignore them. Now, Isabelle is a typed language, so every term has a type. We use a double colon to assert that a term can be given a particular type. So we can read this as has type or of type. The term command asks Isabelle to check that a term is well formed and well typed. So if I write a badly typed term, Isabelle complains. In most places, Isabelle can infer types. For example, I can write false without an annotation, and the output window shows that it is inferred as type bool. And you can see that we have various base types like booleans, natural numbers, and integers. We also have type constructors like list. A type constructor needs one or more arguments to form a type, and we write those on the left. For example, nat list is the type of lists of natural numbers. And we also have sets and words. The argument to word is just the number of bits that we want. We also have type variables, which we write with a leading single quote, and these give us generic or parametric types. For example, the empty list is parametric in its element type. When we nest type constructors, the constructor applications associate to the left. I've written redundant parentheses explicitly here, but you can see that Isabelle omits them when it prints the type back to us. We have tuples, whose types are written as Cartesian products. Function types are written with a short double-headed arrow, which associates to the right. In this example, we can see that a function of two arguments can actually be seen as a function which takes one argument and returns another function, which takes the second argument. Again, I've written in the redundant parentheses, but Isabelle omits them when it prints the type back to us. We have lambda notation for anonymous functions. For example, this is a function taking two arguments, x and y, and returning their sum. Isabelle gives us various ways to define our own types. Today, we'll need data type definitions. You might know these as tagged unions or variants. This example defines a new type constructor optional, which is generic in a single type parameter. It also defines two new value constructors, none and sum, which we use to make values of the new type. None takes no arguments, so it's an optional value by itself. But sum is defined to take an argument, and that means it has a function type, and we construct a sum value by supplying an argument. The sum value then carries that data with it. If we have a value of our optional data type, then we can examine it by pattern matching on the cases. And for constructors that carry arguments, we get that data back. In a theorem prover, we're especially interested in logical formulas. In Isabelle whole, a logical formula is just a term of type bool. We have the usual logical connectives for implication, logical and, logical or, and negation. We also have quantifiers for all n exists. So for all x p of x is true, if p of x is true for any choice of x, and exists x p of x is true if there is at least one x for which p of x is true. Okay, let's look at an example that puts some of these together. This says that for all natural numbers x and y, if x is not equal to y, then there is a strictly positive d such that either x plus d equals y or x equals y plus d. Once again, I've put in lots of redundant parentheses so that you can see the precedence. In the output window, you can see that only one pair of those parentheses were necessary. For example, we can see that equality comparisons have higher precedence than logical connectives. Now, perhaps you can convince yourself that this is true, but let's see if we can convince the machine. I won't go into details. I'll just say that the most direct way to show that there exists something that satisfies a property is to actually write down a thing that we know will satisfy the property. And the rest of the proof is fairly automatic. Okay, now we're going to have a look at how we write some simple specifications and some proofs about them. We'll start with a really simple program with just a couple of global variables and a function which increments one of them. In C, it would look like this. For our specification, we want something with all of the visible behavior of the program, but in the logical language where we can write some theorems about it. For the global state, we use a record type whose fields mirror the program's global variables. For the function, we have a small problem. The C function modifies the state, but the logical language is purely functional, which means values are immutable. So what we'll do is write the specification as a function which takes the initial state as an argument and gives the updated state as its result. We can describe the specification as a state transformer. With that, we can specify increment as a state transformer that takes I as an argument. The definition uses record update syntax, and this is not a mutation. The syntax means we get a copy of the state record S, where all the fields are the same as S, except count, which is given a new value. The new count is just the current count in state S, plus the argument I. Now that we have our simple specification, we'd like to prove some properties about it. We'll consider predicates on states, which are just functions from state to bool. And we'll use Hall triples to state properties of our specifications. The conventional syntax for a Hall triple uses braces to indicate state predicates, and Isabelle allows us to use that syntax. The three parts to a Hall triple are a precondition, which is a state predicate, the specification, which is a state transformer, and a postcondition, which is a state predicate. We say that a Hall triple is valid if for every initial state that satisfies the precondition, when we execute the specification, we finish in a state that satisfies the postcondition. So for example, if we start in a state where the count is C, and then increment by I, we can prove that we finish in a state where the count is C plus I. One thing to notice here is that C and I are colored blue. That's because they're free variables that aren't otherwise defined. That means the theorem is true for any choices of C and I. Now this doesn't tell us everything we might want to know about our increment specification. What about our extra global? Well, as you'd expect, if we start in a state where extra is E, then we finish in a state where extra is E. Now it turns out that these theorems can be hard to use because the phrasing of the conditions is too specific, so it won't often match what we have in a proof. So another way to express that increment doesn't touch the extra global is to say that it preserves an arbitrary predicate P of the extra variable. Now since P is a free variable in this theorem, we can instantiate it to whatever we need. For example, we can instantiate it like this to get exactly the previous theorem. We can do a similar thing for count, but now we have to account for the change in the value of count. Now let's think how we would actually read this statement. It says that if we start in a state where P is true of the count incremented by I, then after actually performing the increment, P is true of the count. Hopefully that makes it clear. Finally, we can actually do a similar thing for the whole of the state. If we start in a state where P is true of the state with an incremented count, then after performing the increment, we'll finish in a state satisfying P. So this Hall triple is actually the strongest possible statement we can make about our increment specification, since the precondition is always the weakest precondition necessary to establish the arbitrary postcondition P. All of the previous triples are actually specializations of this one, as you can see. Now this might seem a tautological statement since the Hall triple essentially expresses the definition of the specification. But that's okay. The entire point of this rule is to lift the definition into the Hall logic. But this is only feasible for very simple functions. At much higher levels of complexity, the properties we considered are much less obvious, and we use the Hall logic to deal with that complexity. Okay, so now let's turn the complexity up just a little. We'll add a simple function to get the current count, and another which combines the previous two functions. The first new problem is that we have a function that returns a value, and our state transformer type can't cope with that. Remember that a state transformer is just a function from initial state to final state. Now we need a function from an initial state to a pair of a return value and a final state. Since different functions might have different return types, we'll take the return type as a type parameter. This type is conventionally called a state monad. We can now model getCount as a state monad where the return value is the current count and the final state is the same as the initial state. This seems like it might be a common pattern, so let's factor out the function that extracts the return value from the state to make a get function. Okay, so get now takes an argument for the extraction function. And we can even prove that getCount is literally getCount. Our increment specification is like our previous one, where the final state includes an updated count. But now we need a return value, and for that, we just use a dummy value. Once again, we can generalize this pattern, this time to make a modify function. This one effectively lifts a state transformer up to a state monad. And we can prove that increment can be expressed using modify of its state transformer. For our double function, our initial state is S, and we first execute getCount in that initial state by applying it as a function. That gives us a return value C and an intermediate state T. We then pass C to the increment function and finally execute that in the intermediate state T. The result of the increment then becomes the result double. Again, this seems like a useful pattern, so we can make a quite general sequencing operator that takes the two things we want to sequence as arguments. And we can also generalize the type to be parameterized by the two return types. See that f is a state monad returning type quote A, and g is a function taking the value returned by f as an argument, and then returning a state monad with the return type quote B. This operator is conventionally called bind, and the Isabelle library even provides some nice syntax that allows us to make our specifications look like programs. This lemma shows that our previous definition is equivalent to this form. When Isabelle prints the theorem back to us, we can also see that bind has some nice infix syntax. Another important function, although we don't use it in this example, is return. This just returns a specific value without updating the state. The next thing we need to do is adapt our Hoare triples to this new setting. The precondition can still just be a state predicate, but we want the postcondition to consider both the return value and the final state. So we can say that a Hoare triple is valid if for every initial state that satisfies the precondition, when we execute the specification, the return value and the final state together satisfy the postcondition. Let's look at the get function. Get doesn't modify the state, so if we start in a state satisfying some predicate P, then we also finish in a state satisfying P. And, as we'd expect, the return value is given by extracting a value from the state using f. We can also write a rule for get in weakest precondition form. We can read this one as saying that if we start in a state where the extracted value satisfies Q, then extracting that value using get establishes Q. What about modify? This rule says that if we start in a state where Q is true of the dummy value and the state modified by f, then we can establish Q by actually performing the modification. Bind is more interesting. This rule says that we can have a Hoare triple for f bound to g under the assumption that we already have suitable Hoare triples for f and g. Roughly, if f takes us from p to q and g takes us from q to r, then f bound to g takes us from p to r. We need one more rule before we can do a proof for double. This one allows us to exchange a weaker precondition for a stronger one if the stronger precondition implies the weaker one for all states. And finally, we have everything we need to write proofs about double using lemmas we previously proved about parts. We use the rule for bind to break double into its parts, but we don't need to look inside the parts because we already have Hoare triples for those. Both of these rules express that the count is doubled. Okay, let's take a moment to think about where we are, since we're already a fair way into this talk and we haven't yet looked at seL4. Remember that I want you to leave this talk with an appreciation of what the proofs are and what they mean, so I think this introduction was essential to that. Don't worry if you haven't followed every detail. In particular, we're not at all interested in how to read and write the detailed steps of these proofs. For now, it's enough to understand three things. Firstly, we can write a specification as a pure function that takes the initial state as an argument and contains the final state in its result. And we can make nice syntax that makes specifications look like programs. Secondly, we can state properties of specifications using Hoare triples, which assert predicates on the initial and final states. You can think of a Hoare triple as a kind of implication from precondition to postcondition via the execution of the specification. Finally, we can compose proofs of the whole from proofs of the parts. There are multiple dimensions to this, and so far we've only seen composition of specifications using bind. But we also have ways to decompose our preconditions and postconditions. Excellent. We're ready to start looking at the seL4 specification and proofs. We'll start with one of the main results of the invariant proofs, and from there we'll drill down into the specification and a selection of invariants. There will be a lot of detail on your screen, but don't worry if you can't take it all in. I will highlight things and summarize what they mean, so listen for that. The reason we're looking at code is to give you an impression of the real thing, and perhaps some exposure therapy. Ideally, I want to convince you that you could take in the detail with just a little investment in learning the language. Let's see how to open the abstract invariants. If you look at the GitHub repo for the proofs under seL4 L4V, you'll see some setup instructions which tell you to install the Google repo tool, which we use to manage collections of repositories. There's a link to the verification manifest repository, and that has a recipe for performing the checkout. If you follow that, you'll end up with a directory containing matching versions of Isabelle, the C kernel sources, and the proofs in the L4V directory. Inside L4V, we're mainly interested in the spec and proof directories. Isabelle's source files are called theories, and we group theories into sessions. Sessions are described in a collection of root files. If we look inside the proof root file, we can see a number of sessions, but the one that we're interested in is AIMS for the abstract invariants. We can see that AIMS builds on a parent session ASpec, which is the abstract specification. AIMS theory files are found in the invariant abstract directory, plus an extra subdirectory for the architecture-specific theories. Finally, the content of the session is given as a list of top-level theories. Before we can open AIMS interactively, we need to build a parent ASpec session. We set the architecture we want with the L4V arch variable, and build ASpec using a makefile in the spec directory. We can then open the AIMS session with an Isabelle jedit command. The -d option specifies where to start looking for the session structure, and the -r option specifies the session we want to work with. Let's also open an ASpec session while we're here. The AIMS command gives us an interactive session looking at the root file, and from there we can control-click or command-click to open one of the top-level theories. And eventually, Isabelle will show us all of its imported theories in the Theories panel on the right. They will take some time to process. Towards the end of the session, let's take a look at the AIMS theory. Here we can see a theorem, A kernel IMS, which is one of the main results of the AIMS session. This says that the kernel execution, specified by call kernel, preserves the invariants defined by IMS. By invariant, we mean that if the IMS condition holds on entry to the kernel, then it will hold on exit from the kernel. With some additional work, we show that it will then continue to hold at every subsequent transition between kernel and user space. To get that, we also show that user space preserves the invariants. And then if we open the ADT AI theory, we see that we have a state machine that specifies the possible interactions between user space, kernel space, interrupts, and idle mode. This state machine is a bit too complicated for us to cover today, but knowing that it's there helps us explain the side conditions we saw in A kernel IMS. The rest of the A kernel IMS post condition says that on exit from the kernel, either the current thread is running or it is the idle thread. If it's running, then the state machine goes to user mode, and if it's idle, it goes to idle mode. Of course, the only thing that can wake the system from idle mode is an interrupt, and this means that if the next kernel entry is not an interrupt, then we must be coming from user mode, and that means that the current thread is running. Knowing that is important at various points in the kernel. To understand this theorem, we'll need to look at a few things. First, let's look at the type of the specification. If we click through smonad, we can see that it's a specialization of non-det monad. This theory is in the aspec session, so Isabelle won't let us click through to non-det monad. But if we go back to ainvs, we can write a tip query, and then we can click through. As you can see, non-det monad is a little more complicated than the state monad we saw earlier. There are some similarities. In particular, it's a function type, taking the initial state as an argument and returning pairs of return values and final states. But there are also differences. Firstly, we take the state type as a parameter, and this allows us to use the same machinery with multiple specifications. Secondly, instead of getting exactly one result pair, we get a set of result pairs. And this allows us to write non-deterministic specifications. Finally, we have a Boolean flag to indicate failure, and this allows us to write assertions in our specifications. Now let's see how we define the validity of Hoare triples. This is similar to what we've seen before, except that non-determinism means that we need to quantify over the set of possible results and final states. Now let's see how we specify the global state. If we control hover over the lambda s in the precondition, the pop-up shows us the state type, and we can control click through to that. This theory is in the aspec session, so let's switch over to our other Isabelle instance. Here we see that state is a small extension of the abstract state type, so let's look at that. This has several fields, and you can see that some of them have function types. If it helps, you can think of these as arrays. For example, interrupt states is like an array whose elements are IRQ states, and which is indexed by all of the values in the IRQ type. That's a 6-word, so we get 64 IRQ states. IRQ state itself is defined as a simple data type with 4 possible values. Some of these fields are nested record types. For example, machine state specifies some aspects of the underlying hardware. Underlying memory gives the contents of physical memory that is mapped into user address spaces, and that's part of the specification of what user threads can and can't do. Some fields in the state are quite simple. The current thread is just a pointer given by an objref. That's a machine word, which for RISC-V is a 64-word. Now we try to distinguish different types of pointers. An objref is a pointer to an object in the kernel's virtual address space, and a vspace ref is an address in some user address space. So we see vspace refs in the parts of the kernel that deal with user space memory mappings, and objrefs in most other places. To understand what an objref points to, we have to look at the kernel heap, or K-heap. The K-heap specifies the part of physical memory in which the kernel allocates resources on behalf of user space. The type of the K-heap is a function from objref to kernel object option. Remember option from the introduction? Its values are either none or some of the parameter type. So this means that for each objref, the K-heap may or may not contain a kernel object. Now, one thing that we do not model in the specification is the byte-level representations of objects in memory. An object is just an abstract quantity, and the entire object is assigned to its base address in the K-heap. Although objects have a footprint in the C kernel, only the first address of the footprint will contain the object in the specification. So what are kernel objects? Well, these are the resources behind the capabilities that are exposed in the seL4 API. And there are various types of objects. A thread control block describes a thread. The main thing I want you to notice here is that threads can be in various states, and thread states are given by a data type. Notice in particular that when a thread is blocked on an endpoint or a notification, the state contains a pointer to that object. Next, an endpoint provides synchronous or blocking IPC. An endpoint can also be in various states. If an endpoint is idle, there are no threads waiting, but in the send state, there is a queue of senders waiting to rendezvous with receivers, and vice versa for the receive state. The queue of waiting threads is specified as a list of objrefs, which point back into the heap. The list here is just a standard functional data structure. Now we're already seeing some differences with the C implementation, so let's look at how endpoints are defined in the C kernel. This is using our own language for describing bit field structures, and I won't go into that. But hopefully it's clear enough that we have a 2-bit field to describe the endpoint state. But otherwise, all we have are pointers to the head and tail of a doubly linked list. So where is the rest of the endpoint queue stored? Well, if we look at the TCB structure, we can see there are fields for previous and next pointers. And these are used to thread the endpoint queue through the TCB objects. So the representations of endpoint queues in the spec and the implementation are quite different. So why is this useful? Well, the C needs to optimize for efficiency and to work within the constraints on where allocations can be performed. But in the specification, we want to optimize for clarity. The specification also benefits from stronger types and standard functional data structures. If you think about the different representations of endpoint queues, they'll only be equivalent under certain conditions. For example, the C data structure doesn't constrain the pointers to form valid doubly linked lists, but it does imply that the thread can be in at most one endpoint queue. In the spec, we have the converse situation. And so we'll need to prove invariants to show that the actual usage of the structures in the C coincides with the usage in the spec. We'll see one of those invariants later. Now the seL4 API is built around capabilities, so we should look at where those are stored. In the specification, we have C-node objects with a size and a contents. The contents are specified by a mapping from C-node index to cap option. So a C-node is an array of capabilities. The number of bits we need to index into a C-node varies with the size of the C-node, and so we can't use a fixed size word for the index. Instead, we use a bool list, which can be any length, but then the C-node contents will only be some cap for lists of the appropriate length for the C-node. While we're here, notice that if we pair an OBJREF, which points to a C-node, with a C-node index that identifies a capability slot within that C-node, then we have what we call a C-slot pointer. So a C-slot pointer uniquely identifies a particular capability slot among all the slots in the kernel space. Now cap is another data type, and you can see that several of these have pointers to objects, as well as other fields which help determine what rights the capability confers. Okay, I think that's enough about the state, so let's go back to where we began, and now we'll look into the specification of call kernel. As the comment says, this is the main kernel entry point. The kernel receives an event, called EV, and it handles that event. It then runs the scheduler to pick a thread. That might be the same thread or a different one, or it might be the idle thread. And finally, it activates that thread. Now, while the kernel is handling an event, there are several points where we allow the kernel to be preempted by an interrupt. If that happens, handle event returns a special value that behaves like an exception, and in that case, we handle the interrupt. If we look into handle event, we can see that there are various kinds of events: syscalls, interrupts, faults, and so on. We also see that there are several possible syscalls. A lot of kernel services are invoked by a send or a call to a capability, and both of these lead to variants of handle invocation. Handle invocation is a little complicated, but I'll highlight the important parts. We first perform several lookups based on the current thread's registers, IPC buffer, and capability space. In particular, we look up the capability that is being invoked, any extra caps, the list of syscall arguments, and the label that identifies the invocation. This syscall wrapper function contains some plumbing which ensures that if any cap lookups fail, then we fault the current thread. We then perform a two-phase invocation, first decode and then perform. The idea is that the decode function does not modify anything, it only determines whether the invocation can be performed, and if so, what action should be performed. If it can't be performed, the syscall wrapper ensures that we return an error to the caller. Otherwise, we reach the point of no return, and the perform phase takes the action. Okay, let's look at the decode. Here, we dispatch on the type of the capability that was invoked. In the case of an endpoint cap, a send or a call is just a request for inter-process communication. So the only thing that determines whether the send IPC can proceed is the writes on the capability. If we do have send writes, then we don't actually do anything yet, but we return an invoke endpoint instruction describing the operation to perform. Going back to handle invocation, that invoke endpoint instruction is then passed to the perform phase, which leads to the actual send IPC operation. We saw before that an endpoint has three possible states: idle, sending, or receiving. If it is idle or sending, there is no receiver waiting to accept the send. Since we allow non-blocking sends, if there is no receiver and we're not willing to block, then we do nothing. If we are willing to block, then we do two things. We set the state of the thread performing the send to blocked on send, and we add the thread to the endpoint send queue. Notice that the endpoint now has a reference to the thread, and the thread state has a reference to the endpoint. We need the thread to have a reference to the endpoint in case we want to cancel any pending IPC for the thread. The final case is when the endpoint is in the receive state. This means there is a receiver waiting for our send. So we take that first receiver, we remove it from the queue, perform the IPC transfer, and set the receiver to the running state. Now remember, when the sender became blocked, we gained mutual references between the endpoint and the sender. Well, receivers and the endpoints they're blocked on also have references to each other. But now that the receiver has been removed from the endpoint queue and also set to running, both of those mutual references have been removed. This is important for an invariant we'll look at shortly. I think we've seen enough of the specification for now, so let's go back to the kernel IMS theorem where we began. The last major piece we need to look at is IMS. This is the first major bundle of invariants we prove about the abstract specification. We see that IMS is a conjunction of two predicates. We'll look at valid state and see that that's also a conjunction of many predicates. We'll focus on valid p-space, and once again we have a conjunction. So it's already clear that IMS is quite a substantial collection of properties. The first one we'll look at is p-space distinct. This is a bit verbose, but the idea is quite simple. This for all implication asks us to consider any two objects in the heap. X and Y are pointers to objects ko and ko prime. Objbits gives the log2 sizes of those objects, and from that we calculate the set of addresses that would be in the footprint of the object in the C kernel. And we do that for both ko and ko prime. P-space distinct then says that if the pointers x and y are distinct, then the intersection of the two sets of addresses is empty. In other words, objects in the heap do not overlap. Why do we need this? Well, in the refinement proof, we need to show that the representations of objects in memory do not interfere with each other. And this property is an important part of that. Okay, let's move on to p-space aligned. This property also considers the sizes of objects and requires that every object in the heap is aligned to its size. Here, the domain of k-heap gives the set of pointers that actually point to objects, and the k-heap extracts the object at x. Now, it's interesting to compare this with p-space distinct. While p-space distinct is an absolute necessity for correctness, p-space aligned is more like a useful design principle. The idea is that a lot of address arithmetic becomes simpler and more efficient if we can assume this alignment condition. But to be able to assume it, we need to ensure that allocations always respect it. Otherwise, the address arithmetic won't always give sensible results. And this reasoning is reflected in the proofs. We need the invariant to carry what we know about the alignment from every place an allocation occurs to every place we need it to make sense of some address arithmetic. Next, I want to look at valid OBJs. This says that every object in the heap must satisfy valid OBJ. This is a bit verbose, so I'll read it out in more detail. It says, for all pointers PTR in the domain of the heap, so that's the set of pointers that actually point to objects, there is an object OBJ such that OBJ is the object at PTR, and OBJ is valid with respect to the state S and its location PTR in the heap. Now if we look at valid OBJ, we we see that its meaning depends on the object type. So let's look at the endpoint case. That's given by valid EP, and valid EP says that if the endpoint is idle, then it's valid regardless. But if there is a send or receive queue, the queue first of all cannot be empty. Then for every pointer in the queue, there must actually be a thread object at that location. So TCB@ just asserts the presence of a thread. And finally, the same thread cannot appear more than once in a queue. Back to valid OBJ, now let's look at the CNode case, and that's given by valid CS. This has two parts, but we'll just look at the first. This says that every cap in the CNode must be valid with respect to the current state. So how do I get that? This CS here comes from the second argument, which is the CNode contents. Remember, that's an array of caps, so the range of CS is just a set of caps in the CNode. And finally, we have some fancy syntax for cap validity. So let's dig into that. Now we can see that cap validity depends on the type of the cap, and for an endpoint, it's just that the pointer in the cap must actually point to an endpoint object. So once again, EP@ just asserts the presence of an endpoint. So we can see overall, valid OBJs is a collection of basic well-formedness conditions on the heap. In particular, it says that pointers should point to objects of the right types. And there are lots of places in the proofs that rely on this condition. And there's an example of this in send IPC. Remember, we saw that when a user thread invokes an endpoint cap, send IPC has passed the pointer from that endpoint cap. And here, we can see that send IPC unconditionally retrieves the endpoint object at that location. If the pointer in the endpoint cap did not point to an endpoint object, send IPC would immediately fail. Ultimately, we need to prove that the kernel doesn't fail, and in this case, it's valid OBJs that tells us that endpoint caps always point to endpoint objects. The next invariant I want to look at is symrefs. This is a bit more complicated, so I want to remind you not to worry too much about the details. Symrefs says that certain pointers between objects in the heap require symmetric counterparts. We've seen some hints of this in send IPC between endpoints and threads. Whenever an endpoint queue contains a thread, then the thread must have a pointer back to the endpoint, and vice versa. And the states must also match. So if the endpoint is in the send state, then the queued threads must all be in the blocked on send state. Okay, let's drill down to see how this works. First of all, notice that the invariant comes in two parts. State refs of S extracts some information from the state, and then symrefs assert that that extracted information satisfies some property. We'll look at state refs of first. Now this is a function that takes a state and a pointer to an object and returns a set of tagged references from that object to other objects. A reference here is just a pointer that one object has to another, and the tag or ref type tells us what kind of objects and states are involved. Now if we look at how the refs are generated, we see that they depend on the object type. Let's look at the endpoint case. We can see that the refs are just a set of threads in the queue, and they're tagged according to whether they are senders or receivers. Okay, now let's look at TCBs. We can see that a TCB has several sources of references, but let's just focus on the ones generated by the thread state. Those are given by TCB st refsolve. We can see that for threads that are blocked, the refs are the objects they are blocked on, and they're tagged according to the thread state. Again, don't worry if you didn't catch all of the details. The summary is that state refsolve takes the kernel state and extracts just the set of references between objects in the heap, and also tags each reference according to how it's used. Okay, now let's look at symrefs. This condition asserts that the extracted set of references is symmetric. Remember, this st argument is the result of the state refs of S that we were just looking at. Again, glossing over the details, symrefs asserts that whenever y is in the set of references of the object at x, then x is in the references of the object at y. And also, the tags of those references must be symmetric. Symref type here defines which tags are symmetric. For example, when the reference was generated by a TCP that is blocked on send, then the corresponding endpoint must be in the send state. Clearly, the kernel is designed to have these symmetric references, so it's reassuring to know that the specification adheres to that design. But let's also think about what it means to prove symrefs and also where we might need symrefs in the proofs. So let's look back at send IPC. To be able to prove symrefs, we need to ensure that whenever we add a reference, we also add the symmetric reference. For example, when we add a thread to the endpoint's send queue, symrefs forces us to set the thread state to blocked on send. Similarly, if we delete a reference, we also need to delete the symmetric reference. In the receive case, we know that the queued receivers have symmetric references to the endpoint, so we remove those symmetric references by removing the thread from the queue and also setting its thread state to running. Now, where might we need to use symrefs in the proofs? And it turns out we need to use it right here in send IPC. When the endpoint has a queue of receivers, we take the first receiver and extract some information from its thread state. That information is only present if the thread is blocked on receive. If the queue thread was in any other state, this would fail. Again, we eventually need to prove that the kernel never fails, and so we need symrefs here to ensure that the thread in the endpoint's receive queue is actually blocked on receive. Okay, we've now seen two places where we need some invariants to show that the kernel doesn't fail. But both of these were about quite low-level details of the specification. What about higher-level kernel design? We'll look at just one more invariant, which we need if we want to be able to delete things to reclaim memory resources. And of course, reclaiming memory is important in most kinds of dynamic systems. The invariant is called if live then non-zombie cap, and it says that for any object that is considered live, there must be a non-zombie cap to that object. Before we dig into that, we need to talk about allocation and deletion. For a user thread to request allocation of an object, it needs an untyped capability. An untyped cap gives control over some physical memory, and a user thread can invoke the untyped cap to request the allocation of new objects. In return, it will get new capabilities to the allocated objects. The kernel remembers that these caps are descendants of the untyped cap in an internal structure called the capability derivation tree. As the user thread uses the new caps, the new objects might become linked to other objects in the heap. For example, a thread might become blocked on an endpoint. Now, if we want to reclaim that memory, we'll need to delete the objects in the region. And we initiate that from user space by deleting the caps to the objects. At this point, when deleting each of these caps, what the kernel needs to ensure is that the corresponding object is unused. In particular, there must be no other part of the kernel with a reference to the object. But currently, these objects are linked with other objects that are not being deleted. Imagine if we removed the objects in our untyped region while those other objects still had references to them. This would already break two of the invariants we've looked at, valid OBJs and symrefs. So to make it safe to delete these objects, the kernel performs a step called finalization. And finalization breaks those links in both directions. In fact, finalization is all the kernel does with an object when its last capability is deleted. Once finalized, the object is still present, but it's completely inaccessible and unused. If the user later wants to perform another round of allocation, the kernel can safely zero the untyped region and start again. But the question is, how do we know this is safe? Remember that the capability derivation tree tracks which capabilities are derived from an untyped cap. So when the user requests a new allocation from the untyped region, the kernel can check whether there are any descendants of the untyped cap. If there are no descendant caps, the kernel will not attempt to reclaim the memory. But if there are no descendants, we know that any residual objects in the region have been finalized, and therefore it's safe to zero the memory and reallocate. But this reasoning relies on our invariant if live then non-zombie cap, which requires that live objects still have caps. Now, an object is live when its state implies that there might be references to it. For example, an endpoint is live if it's not idle, because valid OBJs then tells us that it has some queued threads, and symrefs tells us that those threads must have references back to the endpoint. Once again, if live then non-zombie cap requires that live objects still have caps. And we have another invariant that tells us that caps to objects allocated from an untyped region must be descended from the untyped cap. And therefore the check for descendant caps tells us whether it's safe to reclaim the memory. So that tells us why we need if live then non-zombie cap. But what does it take to prove it? Well, there are two cases to consider. Firstly, whenever an object that was not live becomes live, we need to be able to identify a capability to that object. Objects usually only become live as the result of an invocation, which means that the capability was supplied by user space. For example, when a thread invokes an endpoint to perform a send IPC, the thread must supply the endpoint capability for that invocation. The second case is when the last cap to an object is deleted, and we need to show that the object becomes not live before the operation completes. Here the proof involves showing that finalization makes the object not live whenever the last cap to an object is deleted. For example, the finalization action for an endpoint is to cancel all IPC. And we have a theorem here, cancel all IPC unlive, which says that under any precondition, cancel all IPC on a pointer makes the object at that pointer not live. Okay, you'll be relieved to know that that's the last of the properties I wanted to show today, so I just have a few closing comments. My goal here was to lay a small foundation on which you can start to build your own appreciation of what the proofs say about seL4. And to summarize what we saw, we first learned how to write some simple specifications and Hoare triples. Specifications look a lot like programs, but they're written in a logical language and use more abstract functional data structures and aim for clarity rather than efficiency. We then looked at the specification of the seL4 global state and traced through the send IPC invocation. We then looked at a handful of invariant properties, from simple well-formatted properties up to one that supports a major design feature. The specification and invariant properties are the best places to start understanding the what questions. What does seL4 do, and what properties does it have? There are, of course, many things we didn't look at. I would have liked to have shown you the refinement proof that connects the specification to the implementation, but for now you'll have to take our word that that connection is there. It means that all of the possible behaviors of the implementation are permitted by the specification, and it also means that the properties we prove about the specification are true of the implementation. We also didn't look at any of the higher-level security properties or proofs about the CapDL model used by the CamKes component framework. Some final comments on the invariants. Although I haven't highlighted it yet, we did see some examples of how the invariants support each other. For example, Symrefs supports if live then non-zombie cap, because liveness is defined in terms of the state of the object we want to delete. But what we really care about is the references to the object, and it's Symrefs that supplies those. But we also have the converse relationship, where if live then non-zombie cap supports Symrefs. Because if live then non-zombie cap ensures the safe deletion of objects that would otherwise break the symmetric references. This interdependence between invariants is actually very common, and having seen it, you might begin to imagine how these proofs were developed. We don't write down a complete set of invariants before we start trying to prove them, nor do we completely prove one invariant before starting on another. Rather, it's an iterative process of building a coherent set of invariants, adding new invariants as they are needed to support other invariants, or to prove basic requirements like the absence of failure. Sometimes a property turns out to be unprovable, and we're forced to re-evaluate our understanding of the specification and the properties that we expected to be true. We make adjustments and continue the process. And I think this is one of the true strengths of formal methods. The prover forces you to keep going until you have a specification and a coherent set of properties that all work together. I don't think you get that with testing. Once you have that set of properties, you can look at it and say, yes, that confirms our understanding of the thing that we have built. Thank you for your attention. I'm sure you have questions, so please head to the virtual hub and I'll see you there. After the summit, you're welcome to contact me through Twitter or any of the methods listed on my website.